Huang, that's off at the International Conference, and it is my very much great pleasure to introduce her now. She is a senior research scientist at Google DeepMind and an incoming assistant prof at Computer Science Department at IU. She did her PhD at UC Berkeley. I hope I pronounced his name right. And before she did her bachelor's and master's at MIT. Although all of this information was gathered by ChatGPT on the internet in 5 minutes, so I wrote that it's correct.
Very impressive.
Awesome.
I thought I wrote that.
I asked ChatGPT to write it for you. And her research focuses on developing efficient learning models capable of decision making at an infinite scale. Models for embodied agents. And recently she received an outstanding paper award at ICLR. So today, without further ado, I'll pass the stage to Sherry. Very curious to learn about it.
Thanks so much for the nice intro. And hi everyone, I'm Sherry. I'm very happy to be here to tell you about this exciting line of new work that we've done on and that's been out on generative world models for embodied agents. I think the most exciting progress in machine learning or artificial intelligence in the past decade was in 2016, AlphaGo outperformed humans, and more recently, large-scale models being able to generate highly realistic language and videos. And if we were to step back to understand the techniques that empower these advances, AlphaGo was empowered by research happening in a community known as reinforcement learning, where the goal is to have an agent automatically interact with the world and learn through these trial and error interactions without supervision. Now, this only worked when we had an environment for the agents to almost infinitely interact with. And this was only the case when we had really good simulators, such as the game of Go. But then once we go beyond the situations where we have a good simulator, reinforcement learning didn't make a whole lot of impact other than achieving superhuman performance in Go. But more recently, what we saw happening is that internet-scale text and video data being turned into data powerhouses for these large-scale language and video generation models. So my research has been focusing on essentially how can we leverage these internet-scale data to learn simulators of the real world so that we can continue to develop agents while interacting with this learned real-world simulator so that we can solve more problems beyond just a game of Go. And for that, I want to first talk about exactly what would a world model bring us in terms of achieving superhuman performance or abilities. And let's just take AlphaGo as a thought example, right? So how did AlphaGo achieve superhuman performance? Well, because for these intelligent agents, they actually have a way of simulating into the future, right? Because they have access to the simulator and then they can just try out different actions and see the outcome of the game. And then, because the agent knows more about the future, they can now come back in time and optimize the current decision with this additional information about the future. And because the agent knows more about the future, that's why they can perform better than humans. So for this to work, there are two things that are very important. First, the simulator that the agent uses to imagine into the future has to be perfect. And because the simulator is perfect, then the agent can apply these reinforcement learning or planning algorithms to find these optimal actions in simulation. And because the simulator is perfect, these actions found from simulation can directly translate to the real world. But once we go beyond the setting of games, it's actually quite difficult to expect that we have a perfect simulator. For example, the simulators people have in robotics is very different from what real robot looks like in practice. And as a result, no matter how much we work on the algorithm side, these algorithms are usually applied in simulation because they require a large amount of samples, and the decisions found from simulation don't really transfer to the real world due to this lack of a perfect simulator. Of course, you can try to run your robot directly in the real world and learn at the same time, but this is oftentimes expensive and not safe. So the intriguing question is, well, given how much data we've already collected from all of these robots, can we essentially learn a simulator of the real world so that we're kind of back into this AlphaGo regime where we can develop these RLM planning algorithms in simulation, but because the simulator is really good, then these actions can directly translate to the real world. And for now, we're going to define this learned simulator. We're going to call it a world model. with this motivating example, I'll first talk about exactly how we can leverage internet scale videos, especially videos from humans, video from robots, and diverse sources to learn this world model. And second, I'll talk about after we've learned this world model, how exactly can we apply this world model to embodied learning? It's more than just learning to generate videos from the internet, right? And lastly, I'll talk about some of the challenges we've faced along the way of learning this world model, especially around hallucination and our current work in terms of addressing those challenges. So let's first talk about learning a world model from internet data. So this first project was really inspired by this observation, like our speculation that one of the reasons that language model works so well was because text is a unified representation of information. Because if you look at what is on the internet in terms of text, there are these math formulas and code and also human written text. They all have a common format, which is just these strings of text. And not just text as a unified representation of information, text generation is a unified task interface. For example, all of these different tasks that NLP people used to consider, sentence completion, translation, summarization, sentiment classification, and dialogue, chatbot, and so on, all of these tasks are now casted into a language generation task. And because we have a unified representation of information and a unified task interface, we can just pour internet scale text data into the single model, trained using a single objective, which is text generation, and get back a very general model that can complete a lot of different types of downstream tasks. Now the question is, well, text is by no means the entire sources of data on the internet, right? And if you were at NERVS, you might have heard Elias talk about how maybe pre-training is hitting a wall because we're running out of internet text. And so one thing I would want to propose here is that, well, we have all these videos from the internet, and do videos have something in common, right? In the sense that, do they have a unified representation? And also, is there a unified task objective so that we can actually use to train a single model using diverse set of videos? And I want to assert that videos do serve as a unified representation of information, because if you think about it, what are the types of information existing in videos? There is, of course, information on how to perform a physical task. There's information about the physical world, physics, all implicitly captured in videos. And on the task side, let's say if we have the model generate this future frames of execution that corresponds to some language instruction conditioned on the first frame and this language instruction, if the model can generate the motion of cutting peppers, then the model in some sense has learned what it means to cut peppers. And now, still with the same model trained using the same objective, which is future frame prediction, we just change the input. Instead of inputting text, we're going to input these low-level control actions like delta x, delta y of where to move the robot endpoint. And in this case, if the video generation model can still perfectly predict the next frame of what happens after we execute these actions, then the model in some sense has learned the dynamics, right, by just mimicking what the next frame should look like. And another point is that we have all of these simulators producing these large simulated data sets, and nevertheless, we can sort of merge these data into the same model, right? Because simulated data, according to our knowledge of physics, we can actually collect a lot of them, but oftentimes they don't really look realistic, right? So it seems like each data set on its own only offer a part of the puzzle, a piece of the puzzle. Like some data has humans, some data has robots, some data are large in quantity, such as simulated data, but some data are realistic, such as real robots. So the point being that we still have the same objective, right? Even when we have these egocentric videos, maybe from panorama scans and so on, we can sort of turn these camera angles into the effect of moving the cameras in the 3D space and get back this video of what happens when we try to execute this instruction. And even when we don't have any videos, we can still try to predict using the same model, this image conditioned on this language instruction. So the model has hopefully learned some notions of what a frisbee is and what the throwing motion is. So at the end of the day, it does seem like video, similar to text, video is also a unified representation of information. And we've also developed a sort of unified objective for training this video generation model that can absorb data and represent tasks of different kinds. And exactly how we train this video model, we use the diffusion model, and I will briefly talk about some of the background and the changes we need to make to the diffusion model for it to actually work as a world model. So diffusion model essentially is a probabilistic model that works by when we have some clean image, we try to corrupt the signal from the image by repeatedly applying these Gaussian noise. And we try to learn this reverse schedule epsilon theta by minimizing the squared error between the noise we add to the image and the reverse schedule we're trying to learn. And what this allows us to do is during inference, we can just start from some random noise. And by repeatedly applying this learned schedule epsilon theta, we can get back a clean, a new image. And we can further condition this generation process or this noise schedule on some control inputs, such as we want an image of a robot or we want an image of a human. Now, that's a diffusion model for image generation, but what about world models, right? What about video generation? And the first thing about world models is that when we have some image observation as input and some action as input, we want the background to be consistent. Like, for example, if the language instruction is telling us that the robot should be wiping the table, then the background is better stay consistent. And to make sure the background is consistent, we repeat the first frame across time and input that into a diffusion model. And now instead of doing image diffusion, we have an additional time dimension so that this allows us to automatically just sort of extend image generation into video generation by having this additional time dimension. And now notice that after we condition on the first frame, we can sample from random noise and we can condition on this new language instruction, and then we can try to generate the video that corresponds to executing this language instruction, which is wiping table. Now, you can actually repeatedly generate new video by conditioning on the last frame of the previous simulation to try to generate the next video. And you can also, if you want more fine-grained videos, right, video with higher frame rates, what we did is that we can actually condition on these coarse-grained frames into the future and do this temporal super resolution to try to fill in the gaps. So this is on the modeling side. And on the data side, what we did was we gathered together as much of the video data from the internet as possible. So you see some maybe simulated data sets, some real robot data sets, some human data sets as well, like Eco4D, something V2, and so on. We also had these vision data sets like panorama scans, and also these text image pairs that was used to train clone models and so on. And so like I said, right, we just pour these data into the single model. And we weren't sure what's going to happen because like this work really took place during 2023, the summer of 2023. And during that time, there was no Sora, there was no Genie, there was no world models or video generation models being trained. So it was very an experimental process that we decided to do for this project. And I want to show you some examples of exactly what a world simulator or a world model should look like, right? So this is what you're seeing is like some previously already generated videos, but if the server is running, you can really kind of like take a picture of this room and try to upload it to the server and to start to interact with it, right? So the simulator being a simulator, first of all, you need to choose like an observation, right? So in this case, I've already generated some observations for you. So you can choose a scene with a person standing in the kitchen, you can choose a scene with napkin on the table, or scenes with different objects or with robots or different types of robots and so on. Like all of these were created by a single model. And the major difference between a simulator or a world model and just pure video generation is that a world model should support diverse interactions starting from the same initial observation, right? So let's say in this initial observation of the kitchen, we should be able to conduct different types of actions. For example, we can ask the person to go wash hands. And you can see that this is exactly what's being simulated. But instead of washing hands, we can start from the same initial observation and say, let's pick up the ball or cut carrots or dry hands. So you see that the simulation is actually, doing what the language instruction is telling the world model to do. And not just that we can manipulate these objects on the table, but we can even have these navigation instructions because the model was trained on navigation data or egocentric data as well. So we can say, ask the person to turn left. And you see that the person actually turned away from the kitchen and the dining room showed up. So this was very surprising to us because we couldn't even attribute this dining room back to the training data because it was just not there. Like the model really kind of learned what would happen if you turn away from a kitchen, and usually that would be a dining room. And if you turn the other direction, another model sees a wall. So what I'm trying to say is that this is really beyond video generation. This is really kind of using video generation to simulate interaction with this virtual world. And also a simulator being a simulator, it has to support multiple interactions sequentially, right? So let's say if the first step we ask the person to go wash hands, then we need to be able to simulate continued actions such as shut off water after washing hands, right? So the simulation needs to start from the previous step and carry on to carry out the next action. And I really like this example because it really demonstrated the power of training on internet scale data. So in this example, you're seeing like a napkin sitting on the table, but we can actually use language to structure what happens if we remove this napkin. We can say, let's uncover a toothpaste. And again, you can have repeated interactions with this toothpaste after it's being uncovered by having a person pick it up or slide it to a different direction and so on. But using language, instead of looking at toothpaste, you can say, okay, let's uncover a pen. And then let's start interacting with the pen. So this is really saying that all of this notion of what a pen should look like, right? And what a blue pen should look like and what a black pen should look like really came from internet scale data sets. And similarly with many other objects and also many other ways of the interaction, right? Putting one objects on top of the other projects. So like objects. So all of these are data driven because we didn't really force the model to say, okay, when you pinch the pen, the distance has to be smaller between the fingers and so on. It's really just learning from the data set itself. Okay, so yeah, like there are more examples of how you can also generate videos of robots doing different kind of activities, but that will come. I'll talk about more of that in the second part of the talk. But the really takeaway from the first part of the talk is that once we develop a unified representation of the information, which in this case is just pixels evolving in the time dimension, right? And once we have that, and once we have a unified task interface, which is just conditioned on some kind of control input, and then try to generate the future effect in terms of rates of this control input, we can actually get back a world simulator, a world model. Okay, so I think there are a lot of hype around video generation, but they're only really useful beyond just generating games or entertainment media is to really use them to train embodied agents. So perhaps one of the most straightforward way to use this world model for embodied learning is to do reinforcement learning, because reinforcement learning has this promise that if we have some kind of simulator and we can allow the policy to interact with the simulator indefinitely, we're going to get a really good policy. But then what happens is oftentimes the simulator looks too different from the real world, and this is also known as the sim-to-real transfer gap. But now what happens is that we've trained this world model, right? And this is actually what our new simulator looks like. So all of the videos on the right you're seeing are simulated rollouts of this particular RL policy as we're training this RL policy. So because remember, our simulator can condition on both high-level text instruction, it can also condition on low-level actions. So in this case, we're actually including delta x, delta y of where to move the robot endpoint. And then we're just repeatedly rolling out this next frame. And you can see that we're really getting these realistic rollouts that can be used to train RL agents. And what we found is that usually if we can learn this world model, like what the next frame is, and then try to do a bit of RL on top of that, it's always better than just directly using the data set to learn a supervised behavioral cloning policy. So I think the real intriguing takeaway from this is that people have worked a lot on the sim to real transfer, but I believe that the solution to sim to real transfer is to really have a simulator learned from real world data so that the sim and real are pretty much the same. And on the right here, what you're seeing is a zero-shot transfer of the policy trained in this learned simulator and directly onto the real world, performing this new task of pushing the red star towards the blue cube. You see that the model can indeed zero-shot transfer to the front. Yeah.
Sorry to interrupt, but I wonder how you can work.
Yeah, that's a great question. So yes, that's right. You notice that the simulator generation doesn't really give you the reward directly. So we actually used another reward model. So we actually trained a reward model to predict the number of steps to go until task completion. So we had some data sets. We just annotated that data set using the number of steps to go to get that reward. Okay, so in the previous example, we showed how we can use RL to do these simple tasks of pushing block towards particular directions. But let's say we want to perform some long horizon tasks where the task is, let's put all of the fruits from the cabinet into the top drawer, right? And in this case, you can see it's a very difficult task. It involves multiple steps like opening the top drawer, putting one fruit, putting another fruit. So usually RL for these very long horizon tasks is kind of difficult. But remember, we have the world model that can also take in language instructions, right? So what I'm going to propose is that we're going to try to generate the video execution of this language instruction, and we're going to turn that video into actions to control robots. And I'm going to show you the end result, and I will show you how we actually got this video in the next slide. But for now, you can think of we're just having this world model generating this video, which is corresponding to executing this language instruction. So this is the video we got from the world model. You see that the robot opened the top drawer, put banana in the drawer, and put apple in the drawer. So it looks, quite realistic, but the issue is, well, the actual robot hasn't really moved at all. So how exactly can we use this video to control the robot? And it turns out that if we can generate the video very accurately, recovering action from the video is not that difficult. We can just train an inverse dynamics model. And what an inverse dynamics model is that it just it takes 2 frames and looks at the difference between the two frames, the delta, and it learns to map that difference onto some low-level control. And this is a simple task because the difference between the 2 frames is already pretty minimal, right, in terms of the dimensionality. It's really just capturing what has moved in between these 2 frames, and that's usually the robot arm, and just translating that into low-level control actions is a much easier task. And also, we don't really need like human cutoff data or supervised data to learn this inverse dynamics, because you can just turn on the robot. The robot can just randomly move around while collecting video and recording its own actions to collect data to train this inverse dynamics. Anyway, so this is the action we get after we generated the video, and this is after we extracted this action and we try to execute this action on this real robot, and this is what happened in practice. So you can see that the actual robot execution was very similar to how the robot had imagined itself generating this video of performing this task. Now, so to actually get this long horizon video, it wasn't trivial because you can see that there are multiple steps involved, right? Opening the drawer, putting one fruit, putting another fruits. Just by conditioning on this very high level instruction, it doesn't seem like that would be enough for us to get this long horizon video. So there is actually a little bit more planning involved in the space of video and language. So exactly what we did was condition on this initial observation and this high level task description. We asked a visual language model, say this is the task and this is the observation. What should the robot do first? And as a result, we get back some action samples, right, from the VLM. One says you should open the top drawer. Another says you should put banana in the top drawer. And clearly, the first language is good, but the second action is not. And the reason it's not is because the top drawer is not open. So this kind of embodied reasoning is very easy to do once we actually simulate what happens if we were to execute this action, right? So we use the world model to simulate, okay, this is what happens if we try to get the robot to open the top drawer, and this is what happens when we try to put banana in the top drawer. But then because the top drawer is not open, it's just really hard to get a realistic video that actually completes this language instruction, right? So now what we do is that after we get these 2 simulations, we're going to, again, have this reward model trained on this number of steps to go or return to go to tell us which exact video rollout was actually making progress in completing this task. So because, if human look at these 2 steps, we clearly, the top one is making progress, whereas the second one is not. And this is also relatively easy to train a video VLM for making this judgment. And once we've selected the correct branch, you can see that we're only kind of 1 step into the future in terms of completing this overall task, right? But what we can do is we can condition the VLM on the last frame of the good branch, and then ask the VLM, okay, given this is the current state or current observation, what should be the robot doing next? And as a result, we get back another action sample, and we can simulate that action sample, and we can use the VLM to select the branch again until we have this full plan of completing this task, and that's when we use the inverse dynamics to translate these generative videos into robot actions and execute these actions on the robot. But my point being that maybe this can remind you of the AlphaGo example I showed from the beginning of the talk, where we have this very realistic simulator, but it's a simulator so that the agent can actually search broadly, right? Trying out very different actions, trying out different plans, and observe what happens for different types of actions, all in simulation or all in test type compute and so on, by scaling out the search until it finds a good solution, and then it translates that solution into actual low-level robot controls. I want to also give a little bit more intuition as to why we're doing this language and video planning. It seems complicated. It seems like we need to actually, use a lot of video data training this more expensive model. Why don't we just do behavioral cloning, right? And so to give you some intuition and also some empirical numbers. So let's say our task is to really perform this long horizon task of making a line, right? Rearranging all of the blocks on the table so that they form a line. So this is a long horizon task because many actions are required, and also we want to do this for any initial configurations of the block, right? So if you're doing this through supervised learning or behavioral cloning, you have to collect a lot of data with very different initial configurations of the blocks, so that you have enough training data for the BC policy to generalize to arbitrary configurations of the block during test time. And this is very difficult. So going from this high-level description, make a line, and image, to these sequence of low-level actions is very difficult for a BC policy to do. And in fact, when we tried this directly use a BC policy, even though they're fine-tuned from language models, right? So there are these vision language action models that fine-tunes BLM onto actions. It turns out that they didn't really work. Like the task success is really low. And so what video prediction is essentially doing is that it's predicting these intermediate goals, right? Which is actually pretty intuitive, like what would a line look like? And this is, what would a line look like? And also we have a lot of supervision for training this video model, right? Because maybe this is the particular, like the notion of line also exists in a lot of the other videos. So, and oftentimes people have found like, instead of training like a BC policy, if you do a little bit of like temporal abstraction, you do like a goal conditioned BC policy, or you predict into the future, and this usually makes the BC policy generalizes better. So this is some like independent observations from the robot learning community. Nevertheless, it's sort of the benefits sort of came from the same reason. And yeah, once we do that, we see that okay, we can get a little bit task success, but still like generating this video from this high level language description is still kind of difficult. And once we introduce language, we actually introduce one additional layer of abstraction. And what this additional layer of abstraction does to this task is that it's making the task more modular. It's breaking down the task into simpler steps, right? And not just that, I guess the takeaway is that the task success is a lot higher once we have more layers of abstraction. And the real benefit came from both. First, we broke down this task into simpler steps of predicting language and predicting the goal conditioned on this language, and then finally predicting these actions using inverse dynamics or goal condition policies. And not just that each step of the task is simpler, but we also have internet scale supervision for these top two level tasks, right? Like predicting this language, what should be the first step. This is something that BLMs are gradually getting pretty good at. And also like predicting videos conditioned on some text description, we kind of have YouTube data supervision for that. So this is the reason why we want to do planning in the space of vision, video, and language, as opposed to just do behavioral coding. Okay, so that is kind of like concludes the second part of the talk, which is after we've learned this realistic simulator, we should really use it for training embodied agents because they're really serving as like this is what really makes them useful, right? Other than just generating cute videos. And yeah, and then next I just want to talk about, it's not all glories and successes. While we're working on this, there were a lot of challenges, especially around hallucination, and how exactly we're addressing these challenges. So it's interesting because when we were working on this, we saw some hallucination, but we thought, okay, maybe our model wasn't big enough, and we only had like 1 or 2 person working on this project, and it's like a research project, right? And we thought, okay, the industry is going to pick up video generation. They're going to have a lot more people, a lot more data to scale this up. So we thought, okay, maybe hallucination could be solved by scaling, right? And so the Unison work was actually done 6 months before the Sora release. So 6 months later, we saw this video from Sora. We were very disappointed because like, given that they had a lot more people and a lot more data, they still had this like very weird hallucinations on the chair, which is like jump around without a person touching the chair, right? So this is maybe okay for people who want to generate movies or sci-fi stuff, but it's very concerning if you want to use the video to generate that you generated to actually control robots or to be physically grounded. And of course, if you paid close attention to one of these videos I showed you earlier, you also see a lot of hallucination. like the person is supposed to cut the carrot, but like the carrot actually grows into the knife, right? So this is clearly violating physics as well. And I think like while scaling up data or model architecture is one way to, like we've observed that yes, once you have larger model and more data, hallucination usually reduces, but I think it's not the solution. Like scaling is not the solution to completely eliminate hallucination, because there's always a test type action or language description you can come up with that's a little bit out of the distribution of the training data. So the simulation will be a little bit, will be hallucinatory. So I think the real solution to reduce or eliminate hallucination is to really ground video generation or world models in the physical world and through robots. And I'll show you exactly how. So this is our more recent work where we call the work video agent because we're actually using the video as an agent to control robots. And we still have the same setup as before. So when we have some initial text description and observation of the scene, we use the video to generate how should we execute this task, and then we extract actions from the generative videos, and then we execute these actions in the real world, right? And as these actions from these robots being executed in the real world, we actually get two types of feedback, two types of additional signal. For one, we get feedback of whether the execution was successful or not, whether the task was successfully completed. Because for a really good video that is faithful and that is grounded, we should be able to extract actions that exactly reproduces that video when we execute those actions on the robot. And for another, even if the task is not successful, right, we still collected additional data automatically using the robot by trying to execute this action extracted from videos. So it offers both feedback in terms of whether the task was successful and also additional online data collected by the robot to further improve the video model. And we show that usually like the more number of online iterations we do, right, extract video, extract actions and collect data, and then get the data back to the video generation model, improve the video generation model, get back more data. And usually like the more iterations we do, the more we can improve the task success. So I want to maybe next talk about, so like this is essentially talking still like conditioning on high-level task description to generate video, right? Because like I said, there are two modes of using the world model. One is text condition, the other is action condition or low-level control condition. So I want to talk about also like what are within reach for these simulations condition on low-level controls. I think for one thing that's within reach is policy evaluation, in the sense that the data set that the policy induced during inference time is going to be similar to the data that was used to train this policy from the first place. So you don't get too much of a difference between train and test. And for that, we found that, okay, we can actually generate the simulated rollouts, which is what you're seeing on the left, conditioned on this step-by-step action, right? So this is the validation split of some data collected by some robot executing some policy. And we use the training split to train this world model, but then we use the validation split to look at what exactly would rolling out this policy in the simulator look like, compared to the ground truth data, which is what happens when we execute this policy in the real world. And we see that usually the robot controls or like the arm movement is very faithful, but then like the object interaction is not, right? You can see that the bag of chip actually disappeared at the end of the video. And similarly, there are a lot of examples where we can see that like the arm movement, which is in response to this low-level control, right, is pretty accurate, but real object interaction is hard. Like the orange after being taken out, it's still in the drawer, right? So this is kind of like some other kind of hallucination. But nevertheless, I think there's still a lot of value of using this world simulator to first as a sanity check for your robot policy, right? Because running robots in the real world is just so expensive. Maybe the entire lab has 10 students, but only one robot. So instead of directly testing your policy on the real robot, you should try to test your policy always in this generative simulator first to see that it's doing something sensible before deploying them on the real robot. And second, I think what's within reach is really gripper control, because we have a lot more data from once we execute a policy on the robot, we just have a lot more data about the grippers, and that we have with realistic object interactions, right? So what you're seeing at the bottom here is we're just doing a sweep of different kinds of actions. So first we start with like closing and open the ripper, and then like moving down, up, right, left, right. So you can see that this is really following exactly these low-level control actions that we're trying to simulate. And just a point of reference, this is the original video that started from the same initial frame, right? So the model is definitely generalizing to this new control actions, because if it's only memorizing the training data, then it would have just reproduced this exact video, but instead we can actually use these robot controls to move the robot arm to different directions and so on. So I think ripper controls and policy evaluation will be things that we can apply this generative dynamics model, generative simulator for very soon, if not already. And but in order to get really realistic object interactions, I think that's going to be a long way. One of the reasons is probably a lack of interaction data between robot grippers and realistic objects. And maybe also that comes back to the question that maybe each data set only has a subset of objects. Maybe one group is interested in pick and place, so they're only doing things like block shape and so on. So, but then like the simulator trained on this data set would generalize to soft object interactions and so on. So I think the real future for sort of having this more realistic interactions with object is to have a unified action space across different robots, so that we can actually sort of merge data with different objects in them, right? So these are some examples that are sort of like ongoing work that we can actually simulate executions of different robots once we can unify the action space through tokenization. And the observation space is already unified because they're just using pixels as observations. It's oftentimes the action that's a little bit more challenging to get them into a unified action space. I think that one thing that's also quite interesting is we can also generate we can get like sort of videos from different views of the robot. Like in this case, this task I think was like putting the orange cube on top of a green cube. So this is like a block stacking task. But we can generate the video from the wrist view of wrist camera of the robot, right? So not just we can generate first-person view, but we can also generate not just so we can generate third-person view, but we can also generate first-person view. And presumably, given that how much views there are in real-world videos, if we can sort of effectively learn from all of these views, then during test prep we can really sort of generalize to arbitrary new views. And these views are sort of implicitly aligned just through video generation. Okay, so with that, I guess the real takeaway from the last part of the talk is that eventually the goal is to get the world model to be a simulator of the real world. And maybe they're there, maybe they're not, but nevertheless, we have an agent that can interact with both the world model and the real world, and to get the two worlds to communicate, right? Every time there's data being collected, there's additional training signals for the world model until these two, simulated world model and the real world reach some kind of agreement. So yeah, and with that, I want to thank all of my collaborators across many different institutions and also across academia and industry. And yeah, with that, I'm ready to take some questions. Thank you.
Do you think it would be possible to like augmenting the synthetic video by just with the data and the transformer model? Or do you agree that something like digital twin equipped with some physics engine might be, I think, is necessary to realize the synthetic video that actually all the physical laws can be done realistically?
Yeah, I think so. I think having digital twins or these bottom up, I guess for people who don't know digital twins, they're sort of like you can simulate things from bottom up by introducing artifacts and specifying where the artifacts should go and so on. So I think this kind of bottom up approach versus this data driven kind of top down approach offers sort of different types of information that is required to like come together in the world model, because for digital twins or these bottom-up simulators, you have full control. Like you can say exactly what artifact I'm simulating, and you can really get a lot of data, right? Because you have full control over the environment. The difficulty for that is probably maybe the physics isn't as realistic as they could be in the real world. and also the textures, and it's just really hard to get graphics to all look perfect. But I think the question is exactly how would this bottom-up versus top-down data-driven approach of learning simulators be sort of integrated together? I guess so far my only take is through kind of just merging the data, but also when we merge the data, how can we expect that we only take the good part, right? Like we only take the realistic textures from the real world, but also benefit from this large amount of synthetic data. I think that's still kind of like the open question and the challenge part. But presumably not just digital twins, but people from graphics have also been working on this for decades of how to simulate realistic, difficult dynamics like pulling a pizza and what happens to the cheese and so on. So there is a lot of bottom-up knowledge about these systems. I think that should be integrated with the top-down approach of learning just to predict the next frame. But I think like other than just merging them through just using the simulator to create more training data, I don't have better ways for sort of utilizing the best of both worlds.
Are you aware of any like foundation model that currently contains some like physics engine or like those concepts inside?
I do not. Maybe the most closest one might be like 3D related generation, if you consider 3D information as one of those additional information that's not in the pixel space. I think one of the challenges that for a foundation model to be a foundation model, it has to be very general. It has to benefit from data from the internet or data at very large scale. But then for very ad hoc simulators, they have very specific information for this type of simulation. And this information might not exist in other types of data or other types of system. So it's not super clear, whether including this very ad hoc information from this one system is going to benefit other systems. But nevertheless, I think like once we have enough of these ad hoc information and all have a unified way to represent these information, like tokenize this information into some kind of textual representations and so on, and then injecting that into the system, like what we're currently doing, right? Because if we look at the actions, they're also pretty different, like text description versus low-level controls, and each robot has different types of low-level controls. But even if they're different, as long as we have a way to represent these actions, and then we have a way to model, right? Which is next for prediction in this talk, I think there's a great chance that we can actually use these additional informations.
Seems like a lot of should not actually.
I guess, are you saying like the issue arises because I'm trying to generate long horizon videos?
Or more like your actions. It's very niche here. So chances are that probably like some of the data is relevant to the action. Your actions are really very long.
Yeah, I guess I would say like the exact video, like maybe this exact robot doing this exact activity is maybe long tail compared to like the internet distribution. But I guess abstractly speaking, like if just performing these pick up place tasks, there are a lot of egocentric video, ego from ego 4D or something of some people trying to do the same task. So I guess from the semantic point of view, it's not clear if these tasks are necessarily long tail or out of distribution. But I agree that in terms of just the videos themselves, like yes, maybe like this particular video didn't really exist because yeah, when we trained, like I said, when we trained the video model, we actually included all of this data, right? Because this data was not on the internet to begin with. It's data from some open embodiment data set that was collected by a bunch of institutions from academia to try to gather different videos of different robots. So yes, like this data still exists in short quantity, but I guess maybe that's not going to change very fast because we don't really have a good way to collect a lot of robot data.
So my question is actually one close to examples that I'm showing here. The robot that's a great job.
Right.
But then when you get the interactions,
Right.
it's not actually great.
Right.
So this to me seems like some bias issue.
That's right.
Interactions are harder for 1% or less.
Right.
So maybe training on actually the wrong simulated model of all, but actually the data set that's given to you. There is this gap between all the data set. And maybe this that's the nature of the observations that you see with interaction.
Yeah, I think that's a really good insight, and I think that is the real cause of why we can't really get realistic interactions. Yeah, I don't really have good solutions for that, other than just trying to combine, data that are different in nature, like from different robots or from humans. Hopefully, there will be, as we're talking about the scale of all of the data collected by humans, or as future robots, home robots, and so on being deployed, we will get more realistic interactions, or through simulation, through digital twins, or from graphics. Like if we can do these in movies, maybe we have some sense of how to get the exact next frame correctly from more bottom-up approach.
So you talked a bit about breaking down higher level tasks into smaller, more simple tasks. I'm wondering, how does that affect the computational cost of running like the overall simulation compared to just simulation being constructed by a higher level task for that? Does it actually make it more efficient?
Yeah, so we're going through more steps, right? We're definitely paying a higher cost, like similar to if you use O1, or it's taking many seconds to think through things or to do search. I guess at least for the example I presented with the thought bubble at the top of planning. So in that particular example, we're doing open loop planning in the sense that we're generating the entire video before we're trying to execute any action instructions. So I guess you can get a little bit of offset there in the sense that, like, while your model is executing the previous, while your robot is executing the previous instruction, you can kind of like pipeline things to already start searching, because you already generated the last frame of the previous action. You can already start to simulate for what the better action is. I think currently to get these video generation into like a real system, that reacts in real time, it's a little bit more challenging, because generally each of these videos took 10 to 20 seconds or even longer to be generated. So like you can't really just like have a robot waiting there for 20 seconds for the video to be generated without moving at all. But I think like, people will be working on accelerating diffusion models, or maybe better architectures, latent diffusion, or having better latent representations of like these dynamics. Like right now, I'm modeling things all in the pixel space. It's to be general, right? That's the major motivation. But do we want to learn like latent representations of images, or at least compress them, and so we don't have to pay such a high cost to generate videos? Also important.
If I understand, when you generate the next frame of the video, you're only conditioning on the previous frame, right? Not any other frames.
That's a good question. Also, we actually do condition on a little bit of history, because there were cases where there was occlusion, like the robot arm actually covered the object, but like when it removes the arm, like the object just disappeared. That was because, like the model didn't really capture the object was there. So we actually do have a little bit of history. Right now, it's like a fixed number of frames, like 8 frames or 4 frames from the past. I think it should be learned, right? Because it should eventually be able to take a long context to remember things that, if I put the orange in the drawer an hour ago and then open the drawer, the orange should still be there, or somehow preserve this memory. I guess one thing I would say is that usually we found like the more context we give to the model, the more likely the model will overfit to the training data so there's a little bit of a trade-off. Like if you have this almost Markovian model condition on current observation predicting next observation, it's usually the easiest to generalize, but like the more context we give it, like the harder it is to control something.
That's true. So it doesn't have object permanence if it's out, if the inclusion occurs beyond the context.
It's probabilistic, right? So in most cases, the object disappear because like the training data bias, like usually when the arm moves away, there's no object being covered. It's very occasional that there is some object being covered by the arm. So most likely during inference, when we just draw a probabilistic sample, we're gonna see what's more likely from the training data, which is there's no object behind the arm. Yeah.
So commenting on top of that, so would you say the kind of limitation of the simulator in the current setting is kind of related to this, how diffusion models can't really capture this long-lasting context in terms of compact latent form, and so for now, when we generate things, how they interact with each other isn't quite captured yet. So, which is, I guess, ultimately what a simulation does. If we are working with robots, the simulation kind of captures how things interact, and diffusion models so far don't fully do that in long context, and that's kind of why this simulation isn't quite to the point where you can use it for long tasks.
I guess this is not a fault of diffusion models necessarily. I think if you were to do masked video generation or autoregressive video generation, you're gonna see the same thing. I think the context, I think for one is we don't know how long of a context to model because we don't know what are the things that are important that happen. But like if we do know, I think just conditioning on that context, we actually tried like if we include a little bit of history, it's better at preserving objects, right? And then it's not like we don't know how to model object interaction because in the very simple case of just rearranging the blocks on the table, like we almost always get realistic simulations, like wherever the robot, when the endpoint like goes through this object, like the object would turn and so on. So, but maybe you're referring to like these examples of like bag disappear and more dexterous interaction, and I think that's similar to what Juan was saying about the data set bias because we don't have as enough of like compact data frames specifically, right? So the model is more biased to like simulating movements, which happens a lot more frequently. But I don't think, other than partial observability, I don't think there's anything fundamental that's blocking the next frame prediction model from being able to faithfully simulate realistic interaction, given we have a lot of data.
We've probably already thought through this, but would it be helpful if, like, in the agent setting, if the agent was like narrating to itself what it's doing as input to future contexts?
Yeah, I think some kind of memory, right? So like it doesn't have to be visual memory. Like if we have artifact, like if we know there needs to be 6 objects and just law of conservation, like there should be 6 objects. So we can store that information as some kind of textual memory to the system as well.
Well, you could say,
like,
I just moved the 5th object, now I'm gonna move the 6th object.
Yes, I guess having some language either describing like past activity or describing the artifact, like what I was saying, like the scene, I think will be helpful in terms of preserving memory. It's maybe a more compact way to represent memory than pixel frames.
So let's thank her again.